Okay, hello everybody. Good afternoon, all of you. So we'll start with our today's quote. Success is not counted by how high you have climbed, but by how many people you brought with you. That is more important. May reach higher heights, but many are not remembered because they don't follow the second one. So it depends on how many people you brought with you, how many people you have supported, how many people got help from you. So it depends on that. The success depends on that. So as I told, when you leave the world, how many people worry because of that? So that shows the success of yours. Okay, today is the birthday of Wilhelm Maybach. I don't know how many of you came across his name, but whoever is good in IC engines and you study about carburetors, he comes into picture. So he's a German engineer and engine designer who invented the spray carburetor and was the chief designer of the first Mercedes automobiles. At age 26, he began designing cars with Gottlieb Daimler and Nicholas Otto, with whom he developed the four-stroke engine cycle. In April 1882, he joined Gottlieb Daimler in a partnership to produce a lightweight, high-speed petrol engine suitable for vehicles. He invented the float-feed carburetor, in which fuel was vaporized by passing it through a jet of fine spray and mixed with air to produce a combustible mixture of the engine. He designed the first Mercedes car for Daimler in 1901, but retired in 1907 to design and manufacture engines for Zeppelin airships. But his son followed him in producing luxury automobiles. So he has a lot of contribution towards IC engines and automobiles. Okay, today we deal with centrifugal compressors. And before going to that, we will see what we have discussed in the last class. So we have discussed about the basics of turbo machinery. So there, the velocity at which the fluid enters is the absolute velocity of the fluid, and the blade itself, because it rotates, it is the blade velocity, which is 2 pi n by 60. That is omega, angular velocity, but blade velocity is r omega. So that's where you will get the absolute velocity. And because it is rotating, the velocity at which the blade faces the fluid is called the relative velocity. And we have seen what is the relation between absolute, relative, and blade velocities. And each velocity, absolute and relative velocities, they are resolved into three components, three mutually perpendicular components. One is axial, another is radial, another is tangential. So when it enters at some velocity and leaves at some velocity, whenever there is a change in the velocity because of the change in momentum, there will be force in that direction. So there will be three forces: axial force, radial force, and tangential force. So axial force, which is not useful for rotation, is to be taken care of. It is taken care of by thrust bearings. Similarly, radial force, again, it is also not useful for rotation, but it has to be taken care of by either roller bearings or ball bearings. And the third one, tangential force, is the one which is useful for the rotation. Okay, so change in tangential component into mass will give the tangential force. And into radius at which it enters and leaves. Okay, so that gives me the torque. And into omega will give me the work done. T omega will give the work done. And so we will get what is called as the Euler energy equation. And then we have seen what are the general configuration of velocity triangles of turbo machinery. So as I told, V plus U equal to C, that you have to remember. And always the tangential direction will be the base of the triangle. And so that you have to decide whether this is going this way or this way. So that decides the directions of V and C, the absolute velocity and relative velocity, because V plus U equal to C. And it can be inlet triangle or exit triangle. Whatever be the thing, the velocity triangle will be like that. Base will be U and V plus U should be equal to C. It can be inlet triangle or exit triangle. And then we have seen the Euler energy equation can be resolved into three components of energy transfer. And there we have seen what is centrifugal effect, what is impulse effect, what is reaction effect, after defining what is reaction. So reaction we have defined as the change in enthalpy across the rotor by change in enthalpy across the states. And then we have seen what r equal to 0 meant to, and what is r equal to 1. So impulse, pure impulse, what is that, how the velocity triangles will be, and pure reaction, how the things will be, and how the cascade will be. So we have seen the cascade and how to distinguish whether it is impulse type cascade or reaction type cascade, or a compressor cascade or a turbine cascade. So like that we have discussed in the last class. So these things you have to be very, very confident, okay, about the velocity triangles. So then only you can understand all the other things. It's very, very simple as it. And the main thing, the last point, the cascade, you should be in a position to distinguish. Okay, impulse and reaction, I already told. Impulse type of blades are symmetric or bucket type. So it is very easy to draw it. And reaction type, when you draw, you have to see whether it is compressor or turbine cascade. If it is a compressor cascade, the area must be increasing, right? When you go from inlet to exit, so that the velocity will be decreasing. If velocity decreases, pressure increases. So it is a diffusing process. Compressor cascades should have diffusing passes. But if it is a turbine cascade, you have to show that the area at the entry is more and area at the exit is less. So area should be decreasing so that the velocity will be increasing and the pressure will be decreasing. That is accelerating process. Turbine cascade should give me accelerating process or nozzle-like thing. Okay, so this you have to be very, very clear. Okay, so before going to centrifugal compressor, we will see some of the photographs so that you can understand later. Because if you see 3D figures and when I draw 2D, you can imagine it a little bit how it looks like. So this is an impeller. So a stage of a centrifugal, the compressor or a turbine will have a stator and a rotor. But in the compressor, there will be rotor first and stator next. In the turbines, stator first and rotor next. So that you have to remember again. Stage means stator plus rotor. So compressor, rotor first and stator next. A turbine, stator first and rotor next. So usually the stator here usually will be nozzle and the stator here usually will be diffuser. And so as I was telling, compressor, okay, I will not do that because in axial I will do those things. Okay. So this is the rotor or the impeller. It looks like this. And here we have to see these entry will be axial and exit will be here. Okay, at the low radius there will be entry, at the large radius there will be exit. And entry to compressor is always axial. Exit, if axial, it is axial compressor. If radial, centrifugal compressor. And otherwise mixed flow compressor. Okay. Then another thing is the impellers. The rotor is also called as impeller, and stator as diffuser. And we have three types of impellers. Okay, this is hub or that shaft. Okay, suppose this is rotating this way, and the blades at the exit, it can be bent like this. So this bending, if you see, because it is rotating this way and the blades are bent opposite to that, these are called as backward curved vanes. And it can be like this. These are radial vanes. Okay, forget about how it looks like at the center. At the exit, if it is like this, and if they are bent this way, the rotation in the same direction and the blades are also bent in the same direction. So these are forward curved vanes. So now if I show those figures, now what type of vanes are the impeller is this? What type of impeller is this?
So it depends on the direction of rotation.
At the exit, how the blades look like?
Radial.
These are radial
Radial.
vanes, right? You can see they are radial vanes. If I show this, now these are, we don't know, it is backward curved or forward curved based on how it is rotating. Is it clear? If it is rotating in this direction, the blades are bent in this direction, so it is forward curved. Sorry, backward curved. Is it clear what I am telling?
Yes, sir.
Yes, sir.
Yeah, that's it. And so here, uh, so this is one type of impeller. And after the impeller, these are the vanes where these are called diffuser vanes. These are stator, means they are fixed to the casing here. But the flow that is coming out, it goes through the diffuser blades. Okay, so this is impeller and these blades are diffuser blades. Okay, so flow direction is like if it comes like this and then goes through this diffuser. And this is called as volute casing. So there will be increasing area where it is coming out. Okay, this is exit. And here, this is the intake at which it is entering. And so this is the casing, and these are the vanes which we have seen, impeller vanes. Okay, and this is the impeller which is rotating. And the diffuser will be here. This part is diffuser. This is the side view. Okay, and it depends on how you put it. So if it is impeller kept like this will be the front view, and if you see from the side, this will be the side view. Okay, so this is the impeller. So that is whichever is rotating, and here this small one, this is diffuser. So if I see from here, this comes to the diffuser. And this is the volute casing. If you see here, this is a small semicircle and this is a bigger semicircle. Here, from here, it gradually the area increase, and then it goes up. It collects all the fluid, right, from each of the passes, and then it goes off. It collects all them and goes off. This is exit. And the entry of the impeller is called the eye of the impeller. The entry of the impeller is called the eye of the impeller. And here, this part which is bent, okay, so in the impeller, the initial part will be bent very much. I will tell you why it is bent like this. This is called as inducer. Okay. And also, when it is coming, actually there will be a bell mouth. Here it is like a bell mouth. So it takes large amount of air and it gets in a bell mouth shape here, right? And so that I will get large amount of air at a higher velocity. So it actually goes through, and also at the entry, sometimes there may be what is called as, here at the entry, before this entry to the impeller, there may be some veins, which is called as inlet guide vein. Okay, so I will tell you about that also. So usually if I have all the complications in a engine, so a compressor, so I will have first the air enters bell mouth, and then it enters IGV, which are called as inlet guide veins. Then it enters the eye of the impeller, that is the inlet to the impeller. Then it enters the inducer. Inducer is the one, this is called as like transition piece from axial to radial direction. Because it enters axially, then it turns, right? It turns to the radial direction. And then the impeller veins.
So, sir, for
These,
axial compressors, there won't be any inducer.
pardon? Actually, this inducer and impeller, it is integral part. Sometimes the inducer part will be separately cast and impeller vein separately cast, and they are welded together, or it can be a single one. Like that, it will be there. And what is the question somebody asked?
Sir, for axial compressors, there won't be any inducer, sir.
Yeah, that portion is called as the inducer. Okay, so this bent portion, right? If this is the whole blade, this bent portion of the blade is called the inducer.
Sir, for axial compressors, there won't be any change in
Axial
radial
compressor,
direction.
talking about centrifugal compressor only. Okay.
Okay, sir.
Right. Okay, then impeller, and then there is what is called as veinless space between the impeller and diffuser, right? When it is coming out of the impeller and entering the diffuser, there will be some space. Otherwise, it will hit it, isn't it? Between the diffuser and impeller, there should be some veinless space so that it rotates. Okay, so it enters the veinless space, and then it enters the diffuser, and then it enters the volute casing, and then exit. Okay, this is the way it will be. First, it enters the bell mouth, then inlet guide veins, if at all, if it is there. Then eye of the impeller, then inducer, then the impeller veins, then veinless space, then diffuser, then volute casing, and it comes out of the exit.
Sir, could you please show the bell mouth?
Bell mouth, okay, it's the entry. So it is suppose, okay, this is the impeller, right? So, and this is the casing, like this. And here at the entry, it will be like this. Okay, so it takes air from all over.
Okay, sir.
Right? And here there may be IGV. This is bell mouth.
Sir, IGV is optional, right?
What is that?
Inlet guide vents, they're optional. They might be present or might not be present.
It is optional.
It
I
is
will tell
optional.
you what is the use of that. There may be IGV, there may not be IGV. Okay.
Okay, sir.
Okay. This part is and this is shaft. Okay. So this part is inducer, and this is okay, like and this is diffuser, like this. Okay, so this is one CFD result of the variation of stresses and all. Okay, it is. And so here, if you have a single compressor in a jet engine, it will be like this. Just some photographs I'm taking. And if I have multi-stage centrifugal compressor, okay, normally now it is not used, but in olden days they have used this thread. You can see now from the exit is radial, right? And the inlet for the next compressor is axial. So I have to turn it 180 degrees like this. Okay, then only it can enter into the next compressor. So because of that, because we lose a lot of pressure here, so this is not preferred. Is it clear why this the problem with this? So this is a turboprop engine, you can see. So previously we used to have like this. Now, actually, so these are various types of axial compressors. Now this is axial compressor. And presently, if you want large pressure ratio, okay, so what people used to do is instead of having multi-stage centrifugal compressor, which gives me large pressure, but we lose it. And the axial compressor, if you want a large pressure ratio, you have to have so many stages. And if I have few stages of axial compressor combined with centrifugal compressor here, right, I will have very large pressure ratio. And not only that, mainly centrifugal compressors, why they are not preferred is because of the frontal area. Okay, suppose I will show you. When you compare centrifugal and axial, just we will make that. Centrifugal versus axial. Okay, here high stage pressure ratio. Okay, so usual normal 4:1 and can be up to 6:1 using titanium blades. For high stresses, if I can use the blades which can withstand stresses, I can go up to 6:1. But axial, low pressure ratios. So it will be some 1.14, 1.3. Okay, that's small pressure ratio. But here, multi-staging cannot be done. Any number of stages. Therefore, if overall pressure ratio cannot be met by single stage centrifugal compressor, we go for axial compressor. Okay, so if I want some 10:1, and instead of having 2 stages of centrifugal compressor, you can have some 6 stages of axial compressor like that. So that is preferred. And another important thing is, so an axial compressor will be like this, and you will have a rotor, stator to the casing, and a rotor and a stator. Like this, I will have number of stages, and air enters like this, and leaves like this. And so if I have a centrifugal compressor, if I have some mass flow is equal to rho A C. Okay, so CA I can say because it is coming axially like this. So if I have some axial velocity and density Okay, with the same density and axial velocity, I want to have an axial compressor or a centrifugal compressor. So if I want this much of inlet area, and if I have a centrifugal compressor, and it will come like this. Okay, if this is the inlet area, you can see how much is the exit area. But here, inlet area and exit area are almost same, or sometimes it will be converging also, because it is getting compressed. The last blades will be smaller and the initial blades will be taller. Okay, so frontal area is very high for the same mass flow. Is this point clear? This is very important. Okay, that's why in aircrafts, axial is preferred. But in industrial gas turbine, in industrial applications, where pressure ratio is less than 5, right? We always prefer centrifugal compressor. Here, frontal area is not a problem. In industrial applications, frontal area is not a critical issue. But in aircrafts, right, frontal area should be small. Is this clear? Any point, if you don't understand, you ask me. Okay, so when I have very large pressure ratio, initial stages can be axial stages, and when the area gets reduced, then I can have, right, a small centrifugal compressor. So now whatever pressure is here, that will be multiplied by 4 times. So I can have very high pressure ratio. And because this is inlet gets reduced, exit also can be reduced. Compared to this inlet area, now inlet area is small. So I can go for centrifugal compressor. So this is the way we can have. So you can see axial compressor, it is decreasing area. The last stage will be very small blades. And here if I can have an impeller, right? So anyhow, frontal area somewhat increases, but not much. So you can, this is called as axial centrifugal compressor. Axial centrifugal compressor. So I can have centrifugal stages like this, and axial here, and centrifugal here, like this. This is the way I can have. Okay, when I compare the other things, okay, I'll go to the next page. Here, this is very simple to design, fabricate, maintain, and cheaper. So this is costly, difficult to design, fabricate, so all these things. And okay, so mass flows, here mass flows are very high. We have seen that for the same, this is a low mass flow. Always in turbo machines, the mass flow and pressure ratio are had developed are inversely related. So whenever a machine gives large pressure ratio, it carries only less mass flow. If it carries more mass flow, the pressure ratio will be less. They are inversely related. And also if you see, power is equal to gamma QH. Okay, so gamma is the specific weight and Q is the volume flow and H is the head development. Okay, for a given fluid, gamma specific weight is constant. So Q and H are inversely related, volume flow and head development. Head developed is pressure ratio, volume flow represents mass flow. So they are inversely related. And coming to efficiency, axial high efficiency, and this will have low efficiency. Okay, axial compressors have it. And another thing is the range of mass flow. Okay, how it looks like is, suppose if this is the mass flow, and if this is the pressure ratio. Okay, so this looks a bit like this. So this is something like axial, and this is like centrifugal. So here the range of mass flows. Okay, so the range of mass flow for axial compressor is narrow. Range of mass flow is narrow, and here range of mass flow is wide. Okay, the operating mass flow range is wider for centrifugal compressor and narrow for axial compressor. That is another reason why we prefer in industrial applications, right? So we may change the mass flows very much, but for aircrafts, because the cruising speed is constant, the mass flows are almost constant during the cruising. So that is the reason we prefer centrifugal for industrial applications. And another reason why this is useful for industrial applications is it has what is called as self-cleaning characteristic. And contaminated fluids or slurries, muddy like things, okay, so can be used for with centrifugal compressor. Any type of horrible fluid also can be used with the centrifugal compressor, because what happens is, so when I have blades, whether it is backward, forward, or whatever it is, so it throws away. Nothing gets stuck to the blade, right? It throws by centrifugal force. And the blades also, because they are very simple blades, no problem. Even if something stuck also, it will not be a problem, but it will be thrown away. But when you come to axial compressor, where I have aerofoil blades, and centrifugal effect is not much. And if there is some mud or something stuck to the blade, the profile changes if something is stuck. And because of this, the performance falls. The performance falls. Is it clear? So if you see centrifugal compressor, for low flow and high pressure ratios, they are applied and preferred in industrial applications. And it has self-cleaning characteristic. It can be used with any type of fluid. And it has wide range of mass flows it can use. Only thing is efficiency is a little bit low, but the manufacturing, the maintenance, the fabrication, all these things, they are cheaper and widely used. So these are the advantages with centrifugal compressor. Any questions? Okay. Okay, then now we concentrate on centrifugal compressor. And we have a rotor or impeller, and then a stator or diffuser. Okay, so work is given here. Work is given to the rotor. So work is negative because this is connected to the shaft. So by shaft, work is given to this. So because of this, okay, and okay, if you take the first law, delta Q is equal to dH naught plus delta W. Okay, so for a compressor, delta Q is 0. I am not heating it or taking away any heat or anything. So delta Q is 0. So delta W or W is equal to minus dH naught, or W12 is equal to, if I take like this is impeller and this is diffuser, and before impeller if I take state 1 and after impeller state 2 and after diffuser state 3. Okay, so W13 is equal to H03 minus H0, minus of H01 minus H03, so H03 minus H01. H03 will be large because I am giving some work to this, so H01 will be less, and H03, so this is equal to Cp into T03 minus T0. And so here, because W is negative, H0 increase. H0 increase. Okay, I will put actually not 3, not 2 minus not 1. Okay, that is better because completely it is given to impeller. I will write T02 minus. Later I will tell you it is equal to T03 minus T01 also. Okay, so T0, H0 increases, means T0 increases. So total pressure also increases. I will show you the TS diagram also. And so here the static pressure increase. So if pressure increase, density increase and temperature increase. So this is the way it happens. But in the diffuser, there is no Q, Q equal to 0, W equal to 0. So H0 is equal to constant. H0 is equal to constant because it is a diffuser, like a nozzle or a diffuser, intake diffuser we have studied, right? In the same way, H0 is constant. So T0 equal to constant. So in the diffuser, what happens if you remember intake diffuser again, T0 remains constant, but P0 may decrease if there is friction. Okay, so entropy increases. Usually there will be friction, so entropy increase and P0 decrease across the diffuser. But here, there will be increase in the kinetic energy. Whatever work is given, so that increases the velocity of the fluid. So absolute velocity increase. that is C2 greater than C1. But actually what I want is, I want to have more pressure but not kinetic energy. That's why the diffuser is used, because C2 is very large. So here I use the absolute velocity decrease, and because of that pressure increase and density increase, temperature increase. So this absolute velocity is converted to pressure energy in the diffuser. So this kinetic energy is converted to pressure energy. That's why it is diffuser. And because T0 is constant, T02 equal to T03 across diffuser. Because T0 here is constant. So this can be written is also equal to Cp into T03 minus T01. This is the work done. That is per unit mass flow. This is kilojoule per kg. Like this. If you want power, m dot into Cp into T03 minus T01. Like this. Okay, these things we have to understand and be clear about it. And coming to, okay, this is like this. And here you can see, because the same figure is given here. This is the axial compressor and this is the centrifugal compressor. Okay, and these are the turbines which run the compressors. So this is the difference between axial flow compressor and centrifugal compressor. So you can see that the frontal area will be large. Now you can see this is the inlet, bell mouth will be like this. This is IGV. This is IGV. And this is the impeller. Okay, actually it should be written like, drawn like this, and this part is the inducer and this is the impeller blade. And diffuser, there are actually diffusers, there are two types. What is called as vaned diffuser, then vaneless diffuser. Okay, whatever I have shown previously, the okay, here these are veins are there. Okay, I need not have anything. Suppose these veins are disappeared. So what happens? The area from here to here, because the radius increases, there will be increase in the area. So what happens is it gets diffused. In the area increases means velocity decreases and pressure increases. So that is vaneless diffuser. But if there is sudden diffusion, as I told many times, diffusion means adverse pressure gradient. So there will be disturbance or losses will be there. It should not be sudden. So if it is gradually diffused, then the efficiency will be better. That's why sometimes they use vaned diffuser. Okay, so vaned diffuser, it will have high efficiency and low losses. This is low efficiency and high losses. But vaned diffuser is expensive because I have to design the blades and I have to fix the blades there. I have to fabricate all those things. Vaneless means just increase the space, that's all. There is nothing else. So sometimes depending on the application, the cost that you want, you can have vaneless diffuser also. So here, if there is a diffuser, vaned diffuser, I will have a blade here. But if it is not there, it is vaneless diffuser. Okay, so this another thing is I will tell you. Okay, this part is inducer, as I told. These are impeller vanes. Okay, this is you can see this is vaneless diffuser. There is no vane here. If you have vanes, this is vaned diffuser. Okay, this is again the mouth IGV, and this is the inducer, and then this is the impeller section. You can see all parts. Okay, this is called as shroud. This casing in which it is rotating, this is called as the shroud. Shroud means a cover-like thing. And here for the impeller, the lower part is called as hub, the upper part is shroud, or tip also. Sometimes we call it as tip. This is tip of the eye. This is eye tip. This is called as impeller tip. So you have to be careful about the notation or the terminology. Okay, this is the shroud. And this is eye. And okay, if this is the part it enters, this is called as eye hub. This is called as eye tip. And this is called as impeller tip. Okay. And so the diameter or the radius, okay, this is D1, inlet diameter. And this is exit dia or impeller dia. This is equal to D2. And at the inlet, I hub dia is equal to DH. And I tip dia is equal to DT. And okay, this is D1. That is D1 is equal to DT minus DT plus DH by 2. And DT minus DH DT minus DH is 2 times the eye height. Okay, H I can take. Height of the blade here. And so if I want mass flow, rho 1, A1, CA1. And rho 1, this is equal to pi D1, H1, CA1. I can write like this, or rho 1 into pi dt square pi by 4 dt square minus dh square CA1. Like this I can write. That is the annulus area. Okay, the blades are there in annulus way, and if it is going like this, outer diameter is dt, inner diameter is dh, between which I have the inducer blade. Through this annulus area it is going. So pi into dt square minus dh square by 4. And so this can be written as dt square minus dh square by 4 means dt plus dh by 2, dt minus dh by 2. So dt plus dh by 2 is d1, and dt minus dh by 2 is h1. So this becomes d1 h1. That is what here we get. Okay, so this is the way we get it. This a1 is the inlet area. And if this is d2, And this is called as impeller width at the exit. This is B2. Impeller passes at the exit. Okay, so here this is like this, the whole circumference, it will be like this. So what is the area through which the flow is coming out? So flow is coming out like this. So what is the area through which it is coming out?
Pi d2 into b2.
Yeah, that's right. So if m dot is equal to rho to a2, and here the direction is coming is cr2, the area perpendicular to the direction of velocity, or the velocity perpendicular to the area to which it is coming. So the component is cr2, and a2 is pi d2 b2. So this is mass flow, and this is the at the exit, and at the inlet I can use this, or I can use this based on what data is given. Is this clear? Okay. And another thing, coming to the TS diagram. So if I have this is one, if I have impeller exit here, 1, 2, 3. It is like this for static conditions. If I want stagnation conditions, so at 1, I add C1 square by 2Cp. So I will get 0.1. Similarly, at 3, C3 square by 2Cp. C3 will be almost equal to C1 because C2 will be large because I am giving work, and in diffuser I convert that kinetic energy to pressure energy. So again C3 will be small only. So C1 and C3 are almost same. So this will be 0.3. And so if I do like this, this is 0.3 dash. And so we have seen that T02 equal to T03 because diffuser. So T02 should be same, means T02 should be here. So here it will be 0.2. So what is this then? This is C2 square by 2Cp. You can see that C2 will be large, and that will be reduced to C3 in the diffuser. Okay. So if I take compressor efficiency, this is equal to T03 dash minus T01 by T03 minus T01. Okay, that's what normal. Okay, I will put here like this. Okay, so this line, and this line, if you see, it is like a compressor we got in jet propulsion or gas turbine, like this. Okay, so like this. And so T03 dash minus T01 is equal to eta C T03 minus T01. Okay, so T03 dash is equal to T01 plus eta C into T03 minus T0. And this T03 minus T01, because W is equal to Cp into T03 minus T01. So this can be written as W by Cp. And dividing by T01, T03 dash by T01 is equal to 1 plus eta C W by Cp T0. And we are interested in pressure ratio. So P03 by P01 is equal to T03 dash by T01 to the power of gamma by gamma minus 1. That is equal to 1 plus eta C W by Cp T01 to the power of gamma A by gamma A minus 1. This is pressure ratio. But here now the task is, what is W? W I want in terms of velocities. Okay. So before going to that, we will see the velocity triangles for different types of impellers. So we got backward curved, radial, and forward curved. Okay. And another thing is, we know that from the Euler energy equation, W is equal to U2CW2 minus U1CW1. Okay, I can write U1CW1 minus U2CW2, but it will be negative, right? Because I am giving work, U1CW1 will be less and U2CW2 will be more. So I am writing like this. So here at the inlet, C is axial, means C1 equal to CA1, CW1 equal to 0. If it is axially entering, there will not be any tangential component. So CW1 is 0. If CW1 is 0, this will become U2CW2. This will go off. Okay. So now I want to see how the velocity triangle exit will be. Because now CW1 is not there, I will not draw inlet velocity. Inlet velocity triangle I will discuss later. First we will see how the exit triangle will be. It is like this. And I told you the blade velocity will be horizontal. And again, if you want to draw the velocity triangle with base down or up, it is left to you. Okay, normally base down will be better. So I will draw like this. Okay, and this is rotating in this direction, means left to right. So this is U2, I can write. And what is velocity direction? Velocity direction is in this way. And V plus U equal to C. Okay, so it is this way. It is going like this. I have to add V2 to U2. Okay, so V is in this direction. And if I add these two, I'm going to get C2 here. Any doubt you ask me, right? That is C2. And if I draw vertical, and at the exit, because it is going radially, axial component will not be there. Okay, and so this is equal to CW2. This is equal to VW2. And this angle is the angle of the vane angle at the exit. So this is beta 2. Relative velocity angle is always equal to blade angle. So blade angle is beta 2. Beta 2 is vane angle at exit. This will be always equal to relative velocity angle. That you have to be careful. Okay, so and this component is CR2, radial component, or VR2. Okay, this is the way the exit triangle will be for backward curved vanes. Okay, now if I have radial vanes like this, and again if I draw U2 like this, same length, and how will be V2 now? V2 will be vertically coming out, and this angle is 90 degrees. Beta 2 is here less than 90, and here V2 will be like this, and this is beta 2 equal to 90 degrees. Again, if you add these two, I will get C2. V2 equal to VR2 equal to CR2, and U2 equal to CW2, and VW2 is 0. Like this. Anything, any doubt you ask me, right? Now if I have forward coordinates, like this. And again, this is U2. And V2 will be going in this way. So like this, V2. And this is beta 2 greater than 90 degrees. And adding these two, I will get C2. Again, if I draw like this. So here U2 equal to CW2. Here CW2 equal is less than U2. Here CW2 is U2. Here CW2 is greater than U2. And this is VW2. And this vertical one is VR2 or CR2. Okay, this is the way the exit velocity triangle will be. Okay, and so here I will write CW2 is equal to, you will see the first triangle, I will write it as U2 minus and this particular one is VR2 cot beta 2 because cot beta 2 is VW2 by VR2. So VR2 is nothing but CR2. Okay, so VW2 is CR2 cot beta 2. I will write like this. And you may think why I am using backward chord vane. This is true for radial vane and also the forward chord vane also. Why? Because if you take this, okay, CR2 cot beta 2. What is beta 2? Beta 2 is 90. What is cot beta 2? 0. So CW2 equal to U2. This is right. So if I come to here, beta 2 is more than 90. So what happens? Cot beta 2 will be negative. So CR2 cot beta 2 minus CR2 cot beta 2 will become positive. So CW2 is equal to U2 plus something I will get. So I will have more. CW2 is greater than U2. So this is true for all the three triangles. Is this clear?
Yes, sir.
Okay, so now W is equal to U2 CW2, right? U2 into U2 minus CR2 cot beta 2. U2 minus CR2 cot beta 2. So if I draw okay. So if I write this as U2, I take common and I write it as U2 square into 1 minus CR2 by U2 cot beta 2. Like this. And CRT is a component which represents flow. Okay, here again I will write this as W by U2 square is equal to 1 minus CR2 by U2 cot beta 2. Okay, this is non-dimensional work. And this CR2 by U2, this is also non-dimensional and this is flow component of velocity. It gives the flow, right? So this is what is called as flow coefficient. And this is called as work coefficient. So this is written as psi is equal to 1 minus, okay, psi 2 is equal to 1 minus phi 2 cot beta 2. Okay, flow coefficient is phi 2 and the work coefficient is psi 2. Okay, this is the way they are related. And this is true for all the three machines. Okay, this is like head, this is like flow. So whenever you draw a graph for a pump or a compressor or anything, head flow characteristic we will say. Head in the y-axis and flow in the x-axis, or non-dimensional work coefficient versus flow coefficient. Like this we will draw. And so psi2 is equal to 1 minus phi2 cot beta 2. If I take like this, and if I draw a graph between phi2 and psi2, okay, and when there is no mass flow, phi2 is 0, so psi2 is 1. It will become, okay, something. Okay, so as mass flow increases, if I take a backward curve when beta 2 is less than 90, so cot beta 2 is positive. So what happens as phi increases, this is negative, it becomes negative and psi decreases. Am I clear or not? Cot beta 2 is positive. Phi to cot beta 2 is positive. As phi increasing, the phi to cot beta 2 increases. So 1 minus that decreases. Is that clear?
Yes, sir.
So it decreases and decreases and decreases like this. This is backward curve. As phi increases, psi decreases. Suppose if I take radial, beta 2 is 90, whatever be the flow. So beta 2 90 means phi 2 cot beta 2 0. Psi 2 is 1, whatever be the phi 2. So it will be like this. This is for radial vein. And if you see forward compress, the forward curve, beta 2 is greater than 90, cot beta 2 negative. So phi 2 cot beta 2 negative, and 1 minus of a negative quantity means plus. So for any phi, I am adding something to psi. As phi increases, the addition increases. So I'm going to have something like this. Is this clear?
Yes, sir.
So this is the general way I will get. Actually, I will stop here. I will continue in the next class. Any questions till now? Okay, I will. So parts of centrifugal compressor: impeller vanes, hub, shroud, inducer, diffuser, like that. So this is single entry compressor, and sometimes there will be double entry. And this is single entry shrouded. Okay, so they will be covered like that. And these are radial vanes, these are backward vanes and forward vanes. So it will be something like forward, I will have obtuse triangle, and radial, I will have right angle triangle, and backward, I will have acute triangle. So if I draw the pressure ratio and mass flow rate, so backward will be like this, radial will be like this, and forward will be like this. Okay, the remaining things I will explain in the next class. Okay. If there are no questions, we will go for the story. Okay.
Yes, sir.
So this is an interesting and a little bit touching. The most important part of the body, the story name is. Okay, so it is narrated by one person, and he says, "My mother used to ask me what was the most important part of the body." So from his childhood, normally she used to ask whenever some opportunity comes, okay, what is the most important part of the body? Through the years, I would take a guess at what I thought was the correct answer. When I was younger, I thought sound was very important to us as humans. So I said, "My ears, mommy." And she said, "No, many people are deaf, but you keep thinking about it, and I will ask you again soon." And several years passed before she asked me again. Since making my first attempt, I had contemplated the correct answer. So this time I told her, "Mummy, sight is very important to everybody. So it must be our eyes." She looked at me and told me, "You are learning fast, my son, but the answer is not correct because there are many people who are blind. Stumped again, I continued my quest for knowledge, and over the years, mother asked me a couple of more times, and always her answer was, "No, but you are getting smarter every year, my child." Then one year, my grandfather died. Everybody was hurt. Everybody was crying. Even my father cried. I remember that especially because it was only the second time I saw him cry. My mom looked at me when it was our turn to say our final goodbye to my grandfather. At that time, she asked me, "Do you know the most important body part yet, my dear?" I was shocked when she asked me this now at this situation. I always thought this was a game between her and me. And she saw the confusion on my face and told me, "This question is very important. It shows that you have really lived in your life. For every body part you gave me in the past, I have told you you were wrong, and I have given you an example why. But today is the day you need to learn this important lesson." She looked down at me as only a mother can. I saw her eyes well up with tears. She said, "My dear, the most important body part is your shoulder." I surprised. I asked, "Is it because it holds up my head?" She replied, "No, no. It is because it can hold the head of a friend or a loved one when they cry. Everybody needs a shoulder to cry on sometime in life, my dear. I only hope that you have enough love and friends that you will always have a shoulder to cry on when you need it." Then and there, I knew the most important body part is not a selfish one. It is made for others and not for myself. It is sympathetic to the pain of others. People will forget what you said. People will forget what you did. But people will never forget how you made them feel. Thank you. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you. See
Thank
you.
you, sir.
Yeah.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Excuse me, sir.
Yes.
Sir, if the LMS will not allow us to submit the assignment, then can we mail you the third assignment?
No, maybe. How many of you had to submit?
Sir, third assignment.